substitute for fx of x. Substitute for fx of x. So you can substitute this one here. So summation I is equal to 1 to n pi into delta of x minus xi into e to the power of j omega x into dx. E to the power minus j omega x into dx. Okay. Now let us interchange the order of the integration and the summation here. So do that one. Interchange the order of the integration and the summation. Okay, so if you do interchange, so it will become summation I is equal to 1 to n. So pi, let us take separate here. The remaining quantity is nothing but, so integral from minus infinity to plus infinity. So delta of x minus xi into e to the power of j omega x into dx. E to the power of j omega x into dx. So already we have the time shifting property. So from time shifting property, we can apply this integration. So this is equal to the e to the power of j omega xi will get here. So this will become summation I is equal to 1 to n pi into e to the power of j omega xi will get here. This is as per the time shifting property here. Okay, so this is as per the time shifting property. So this one you are going to get here. So that is pi x of j omega is equal to, so this is the, for the discrete random variable, we can define the characteristic function like this. We can define here. Okay. Done. Okay, this is some function we are defining.
Yes, sir.
Yeah, so nothing else we are doing here. Just in place of x, we are substituting this as the e to the power of j omega x. We are substituting that here. Okay. So similarly, we can define the nth moment of the this characteristic function. We can define here. So you can take the nth moment of the. So you can take the nth moment of the characteristic function. The nth moment of the characteristic function is obtained from the nth moment of the characteristic function is obtained from differentiating pi x of j omega with respect to the omega, differentiating the pi x of j omega with respect to omega, we get. So if you're going to differentiate the characteristic function with respect to the omega, we'll get like this. So the nth moment is nothing but, so already we have seen the nth moment of the random variable in finding the mean and the mean square value. Okay, so mean and mean square value. So it will be taken like this. So fx of x. So nth moment is nothing but x to the power of n will come here. So e to the power of j omega x into dx. Okay, so if you are going to set omega is equal to 0. So we'll substitute omega is equal to 0 so that it will become the nth moment. So that one it is called as the e to the power of expected value of x to the power of n. So this one is obtained by, okay, so we are going to set omega to the 0 here. So pi x of j omega. So these are some different kinds of functions we are going to be considered. So I'll tell the application later where we'll get and what's the use of this one. Okay, so fx of x into dx will get here. So you are going to substitute omega is equal to 0. So this will become x to the power of n into fx of x into dx will get here. So this is the nth moment you are going to call nth moment of the characteristic function by setting omega is equal to 0 here. Okay, so take this one. So this is called as the characteristic function for the discrete random variable, and the nth moment we are going to be considered here. Nth moment you are going to consider. Done. Okay.
Yes, sir.
Yeah, so this is a characteristic function here. So now we are going to define one more function which is called as a conditional random variable. We are going to consider here. Conditional random variable is the thing. Already we have seen the conditional probability. Okay, So I'm going to recall that concept. I'm going to define the new function which is called as a conditional random variable. You are going to define here. So conditional random variable is nothing but suppose if the event B has already occurred here, and if the event A is supposed to be occur, so that depends on the occurrence of the event B. So that one you're going to call it as the probability of A given B. We're going to call here. Okay. So similarly, here also we're going to define the conditional probability density function in the same manner. That is the probability of A given B means that the event B has already happened here and event A is going to be happen. So this is nothing but the probability of A intersection B. Okay, so divided by the probability of B. Already we have seen this one. Okay, in the base rule we have seen that. Okay, so probability of B is not equal to 0. So this is called as the conditional probability we are going to call here. Okay, so that is nothing but so the event B has already happened here and event A is going to happen. So that probability is given by the probability of A intersection B divided by probability of B here. So based on this concept, we are going to define the conditional cumulative distribution function and the conditional probability density function you're going to define here. Okay, for the random variable X, we are going to define that concept you are going to define here. Okay, so done that. So take this one. So before taking this one, so let us define in terms of the random variable X here. So you can take let X be a random variable. Let X be a random variable. Let X be a random variable. Let X be a random variable with its probability, with its PDF and CDF, with its PDF and CDF as fx of x, with its PDF and CDF as fx of x, and so this is the probability density function, and fx of capital X is nothing but so this is a cumulative distribution function respectively.